Thanks for joining us today. In this brief overview, I'll discuss our package, MLMOD, for data-driven modeling and simulation in LAMMPS. This is a package that can also be used in conjunction with our SELM fluctuating hydrodynamic package, which provides ways of doing hybrid modeling with continuum fluctuating fields. I'll be giving also a breakout session tutorial on the user SELM package on Friday for those that are interested. So the basic idea of the MLMOD package is we'd like ways of leveraging recent tools and techniques that have been emerging in the statistical inference community. And so just to give one kind of motivating example, we could think of modeling a system with a lot of detail in a LAMMPS simulation, but often for gaining further insight or to incorporate models into larger scale simulations, we're often interested in developing simplified descriptions of the physical system. So on the lower left, I'm showing an example of a colloidal system where we've resolved the solvent degrees of freedom explicitly, but what we're often interested in is the dynamics and interactions between the colloidal particles. And so we're seeking a coarse-grained or reduced order model of this system. And so there are many theoretical tools that have traditionally been used to do this. What I'm interested in is ways in which we could use data-driven techniques to arrive at those models for the dynamic, the potential interactions, and other quantities of interest. And so one way you could, of course, get at this is looking at passive fluctuations of the system, or by actively intervening. In the middle of what I've shown here is simulations we've done where we basically apply probing forces to one particle and we see the response of the other. The aim here, of course, is to get at the underlying mobility. So the typical workflow in such a problem like this would be to start off with your simulation in LAMMPS or in our SELM package, and then use that trajectory data within your preferred machine learning framework, essentially to learn those important response functions. This can be encoded in many different ways. You can pick whatever your favorite model class is, such as deep neural networks. You can use things like kernel regression. And then the basic idea is that any model that you can work with in PyTorch that can be exported to a standardized format can be imported into our MLMOD package, which serves as a fix then to allow for development of data-driven time-step integrators, force interactions, or computing, again, other observables, quantitative interest that for other downstream machine learning tasks, or to gain further insights into the system. And so the basic approach in the colloidal system would be to just estimate this mobility tensor. This is essentially telling us what the force response or velocity response is given the forces acting on the particles for a given configuration. This is has a nonlinear dependence typically on the configurations. Now, while there are theoretical tools that are typically used for the far field, such as assuming pairwise interactions and translational and rotational invariances and equivariances, where this gets interesting is in the near field, where you may have potentially many body interactions, and where a data-driven approach may allow us to develop models that are more accurate. So once one has estimated and encoded this mobility tensor m of x, one can apply tools from statistical mechanics to get the drift diffusion dynamics. So what we're envisioning here is a way in which we can sort of move information and models back and forth between common machine learning frameworks and LAMMPS simulations. And so the MLMOD package provides different modalities for doing that. For more information, you can see the link that I've listed on the middle here on the bottom. You can also join our mailing list where I'll send out announcements of future releases of this package that we're developing. I'd also like to thank the grants listed on the lower left for support of this work and related projects. So thanks for joining us today. I look forward to when we continue these discussions in person.